Okay, let's solve the spine protector problem using explicit dynamics. So I insert this module here. And in engineering data, we define a new material called Agilis. So there are no properties currently available for it. So the first thing to insert is density. So the density of this material was 1,100 kilogram per cubic meter. You can see here we don't have all the options because we have clicked on this field. So if I click back on the material, we can see all the options available again. So in terms of hyperelastic response, I mentioned we want to have a Newhookian material model. The shear modulus of Agilis was 162 megapascals. So I insert that value here. And can see for a Newhookian material, you just need two parameters. One defines the shear response and another one defines the volumetric response. For the volumetric response, we mentioned that we use the value of 1 per gigapascal. So here we insert that value. Well, next we need to define the viscoelastic properties. So again, I click back on the material and I have all the options available here. Not this, not that. So here we insert Prony shear relaxation, which is defined using the Prony series. This is asking for the number of terms. If you remember, we had 3 terms. So if I insert 3, you can see this table is now expanded into 3. If you cannot see this table, you should go here and check this table here. All right, so you can see the tables there. Now we need to define the relative moduli. These are GI. So 0.679. Next one was 0.309. And the last one was 0.009. And in terms of the characteristic time, these are in second. You can change this to millisecond if you like. And insert this 0.1, 0.2, and 100. So actually, again, this shows the highly viscoelastic response of Agilis, which actually makes me a bit suspicious about this performance on their impact here. So probably its performance would be very rigid, but let's see. So now the material has been defined with all the necessary properties. Next, we need to insert our geometry. So we import the geometry. I have already created different geometries for this problem. So this one is the assembly, and I have cut the assembly in a quarter. Why have I done this? Okay, now our assembly is loaded, and as I mentioned, I have cut it in a quarter. Well, the reason is that we have 2 planes of symmetry for material, geometry, boundary conditions, and loading. Hence, we can use symmetry to reduce the size of our model. If we do that, we need to apply boundary conditions that will impose the symmetry, which you will see in a moment. So first, we look at the geometries. One thing that I will do here is that I will turn this, the anvil, and impactor into a rigid material. Why? Because Agilis should be much softer than steel, and therefore I can turn these two into a rigid material so that I can increase the stable time step. You can try it with deformable material, like defining this with properties of steel and not making them rigid, and you will see how much the time step is affected. So this material here, this part is flexible. So this is the way to do it in ANSYS. In other software, it could be a different approach, as well as this one. So the anvil, I make this rigid as well. alright, but I keep the back protector flexible. So we have two materials here, structural steel and Agilis. So you can see for the impactor we have structural steel fine, but remember this will be rigid, so the properties of structural steel will not be used for evaluating the stable time step. And anvil is structural steel as well. So here for back protector we need to change the material to Agilis. Okay, so this is done now. Well, this anvil, if I just continue by setting up the simulation, it will use the mass of the quarter of the anvil, which is this, but there is no guarantee that this mass will be a quarter of 5 kilogram. And in reality it is not. I have already measured the mass of the entire anvil and subtracted it from 5 kilogram and divided the resulting value into 4, and now I'm going to apply that quarter mass on this part as a point mass. So if I go back to the impactor here, and I go back to geometry, I will define a point mass on our impactor. So let's delete this. On the impactor we can insert a point mass, and it tells here ask us to select the geometry. So I believe I can use this place, and here there are the coordinates of the concentrated mass. I'm not too much worried about this because I'm going to constrain this anvil to move along the y direction only, and the only parameter I need to define here is the mass, which is 0.943, and that is accurate enough in terms of kilogram. You can work it out yourself and see how much you should add here. I will provide the CAD files so you can use that and import them here. I provide them in SolidWorks format. You don't need moments of inertia because, as I said, I'm going to constrain this anvil to move along the y direction only. So it's not going to rotate, therefore these properties are not useful. Here the behavior, we turn this to rigid to make sure that these two are coupled. So next you can see connections. So this is where we define contact. You can see there is a question mark next to contact, and this one does not have it. So contact here defines manual contact, surface to surface contact, which when we have a rigid body, apparently in ANSYS we cannot use this option. So I delete this. Instead we can live by this option, which is a general contact. So wherever there is possibility of contact between parts, this comes in place and deals with the contact. So we can see that here actually the bodies are, all bodies are included, and the type is frictionless. We can add friction, for instance 0.3 coefficient of friction, but for this problem I believe it's not going to make much difference, so I'm not going to change this. Next we will create mesh. Here is the mesh. So we have 5 elements through the thickness of Agilis, which is decent enough for us. Now, how about initial conditions? We know that this mass has an initial velocity, so let's select this geometry, which will include the mass attached to it, and apply the velocity in y direction, which was in millimeters per second was 4,472, and this was negative, right? So it is initially it's traveling in this direction. So you can imagine what this is. This actually defines the vector of nodal velocities at time 0, and then leaves it to the software to work out what should be the velocity and displacement afterwards. Yeah, so I forgot to click apply, so now you can see this is fine. Next we need to apply boundary conditions. So the boundary conditions we have, we need to fix the support, which is here, and here I'm gonna use this surface. So essentially it will fix all degrees of freedom of the nodes of this surface. This is a rigid body, so fixing that means essentially no movement at all anywhere. Well, it seems this doesn't work, probably because it is a rigid body we need to use the entire body. Yes, that's right. So then it would be the same for the other rigid body, where we want to limit displacements of the mass here, or of the impactor. So I apply this, and you know that I want to limit its motion in X direction and motion in Z direction, but not in Y direction. So this is actually guided by the rails. This mass in the test is guided by rails and moves straight down. Hence I constrain displacement in the transverse plane. Okay, so that boundary condition is defined as well. What we have not done yet is defining the symmetry for our structure. Okay, I was looking for where symmetry is located, so you need to click on the model, and here you can see symmetry. Okay, so symmetry now is added as another option in the tree, and here I can add symmetry region. I choose this face, all right, and then for this face I apply symmetry normal to z-axis. So essentially by applying this boundary conditions, it doesn't allow nodes on this surface to move in the z direction. They can move in x and y. And I add another symmetry on this surface, and for this one I will fix all the displacement translations in the x direction of all the nodes here. This is essentially what the symmetry is doing. You don't need to worry about the impactor and the anvil, because these are rigid bodies and we have already fixed this one and fixed this one from moving in x and z displacement directions. Okay, fine. So now let's look at our analysis settings. So one thing that we need to define here is the end time. For the end time, I'm going to use 5 milliseconds or 0.005 seconds. I have done this simulation before, so I know what it should be, but you can try it. You can give it some value and see if the simulation is finished. In other words, if the impact is completed, and then you can stop. And reduce this, because having very long duration, of course it needs longer time for doing your simulation and more variables are stored, so both in terms of time and storage this is not efficient, so you need to make it as short as possible. Okay, let's look at some of the available options here. So you can see explicit time integration is being used here. This is what our topic was on. So there's something called energy error. So this is actually linked to what I mentioned about leaking energy from the system. And if this energy leakage is more than 10%, the simulation will stop. You can change this if you like, but you should be very careful with your results. So you can see there is like a safety factor for initial time step. So what I mentioned, L over C minimum, that actually has been multiplied by 0.9. So reduced by 10%, and that is the starting time step, or time step for our simulation. So you can also define it yourself, but it's better not to do it if you don't know what the time step would be. And this is the way that the characteristic length is being calculated, diagonal, for instance, diagonal approach. There is no mass scaling in this simulation, but you can define it. So perhaps nothing very interesting here for us. And you can see here, for instance, under damping. Damping is usually used to deal with hourglass energies. The default in Elastina is using reduced integration, hexahedral elements. Therefore, this damping is being used, and specifically hourglass damping is being used here, and there are two types. So this is the the default option. If it didn't work, perhaps you can go and try the second option, or change it from viscous to other types, or change the coefficients. But you should be very careful with these settings. So it's best to use the default, and if it didn't work, use a different algorithm that is available here. So what else we need to do here is looking at how many time points we are going to write out the results. So here the results are saved at 20 equally spaced time points. We can change this if you like, but I will just go with the default option. So let's solve this problem. When we start the solution, we can click on this option, and we can see the solver output. You see that some initial checks have been completed. This is the time increment. So you can see the initial time step is 1733 nanoseconds. And you can monitor it if you like. You can see how the time step is varying. So you can see the time step has been reduced a bit and increased a bit. So I can tell you that this is related to Agilis being compressed. Therefore, the size of elements have reduced slightly. That has affected the stable time step. And then it has increased, probably because it has rebounded and the elements are back to their original shape. Good news is that the simulation is already done. So we can look at things like energy conservation. So these have certain meanings in LS-DYNA. You can look at the manual here and understand what these energies mean. So you can go to mechanical help and look at that. Something interesting here perhaps is the energy summary. So you can see here that we have the kinetic energy that starts from 12.5 joules. So if you multiply it by 4, it will be 50 joules. So our simulation is correct. So these are the sanity checks that you always need to do after you run the simulation. So the kinetic energy is correct. So we have defined the mass correctly and velocity correctly. And the point mass, for instance, has been taken into account in the calculation here. So the kinetic energy goes down because the mass is coming to a stop and then rebounds. However, internal energy, which is elastic, viscoelastic energies inside the material, it has increased as the material, as Agilis is being compressed more and then released. Interesting is hourglass energy. You can see the hourglass energy has increased a bit, but it is not too awful, to be honest. So it has to be less than 10% of this energy, or maybe the peak of the internal energy. So we can live with that, because at the point where we are interested in, the hourglass energy is actually much smaller than the internal energy. So then let's look at the deformation. So we look at the total deformation. So let's evaluate this. So here it is. You see that this duration is actually quite short. The impactor is hitting the Agilis. Agilis is sitting there, but then both of them rebound off the anvil at a very short time. So around 2-3 milliseconds, they have detached more or less. And let's stop this. So here we can look at the force reaction. And for this one, I'm going to look at the fixed support, which was the base of the anvil. So here you can see the force curve. It goes to the maximum value around 1 millisecond. So we can look at the reaction, the total. So that is the resultant, and the maximum predicted here is 9,442 newtons, or 9.4 kilonewtons. So are you happy with this? Do you think that this is a level 1 back protector? Well, something to be extremely careful about is that we use symmetry. So we cut our model in a quarter. Hence, we need to multiply this force by a factor of 4. Therefore, the force here is around 40 kilonewtons, which is obviously way above even the higher value for level 1, which was 18 kilonewton. So obviously, a single layer of Agilis 2 centimeters thick is not going to pass this standard. So what usually happens is that manufacturers, they make holes inside this structure, make it hollow, make it from lattice, etc., in order to increase the compliance, reduce the stiffness, and increase the energy absorption. But I hope that this example has helped us to review all the theory that we have seen in the lecture and learn how they can be used within one package, which is ANSYS here. Thank you for your attention.